And in today's class, we're going to summarize our studies of advanced function, of polynomial functions by looking into transformations of cubic and quartic functions. This would be part of your unit test that we will conduct this Friday. And talking about that, I wish you good luck at the test, and my personal advice to you, in order to succeed, I suggest you review all the previous classes, look into instantaneous and average rate of change, characteristics of polynomial functions, as well as ways of graphing polynomial functions that we covered in the last week. This week we mostly concentrated on instantaneous and average rate of change. So, returning back to polynomial functions, transformations of cubic and quartic functions. Prior to starting a new... Oh, hello, Lorraine. Nice seeing you. So I was saying that we're gonna have unit test this Friday, and in your Google Classroom, I'll post the practice and exercises in order to prepare for the test. And I'm also gonna mention the topics that this test is going to cover. So before we start our today's class regarding transformations of cubic and quartic functions, I suggest we review one nice short little video on YouTube. They're gonna help you to understand graphing easier, because from my perspective, the most important thing while working with functions is to be able to visualize them without any problem. So let's spend at least 9 minutes to review this material from past classes. Let me know if you have or don't have sound. So please, guys, Lorene, and take a moment to note down the steps because it's a great summary of the class we had last week with Yasser. And this is a general approach on how to plot polynomial functions. And it will be really useful for you to remember the 3 steps because knowing these 3 steps will allow you to plot almost any polynomial function with no problem. Okay, Lorraine? Please take a moment to note down these 3 steps, okay? So I believe this video was informative and I suggest we move on to our textbook. And we're going to talk about transformations of cubic and quartic functions. So you already reviewed on how to plot these polynomial functions. And just give me a second. There is a So just so you know, there is a great software that can help you to investigate properties of graphs and sketch them easily. It's called Wolfram Alpha. Here you just type in the function you would like to plot, and this beautiful software is going to give you some additional information about it, as well as a graph of this function. This is widely known and used software, so please get familiarized with it. It will be helpful for your future studies. So, and let's start. The graphs of the parent cubic function y equals x cubed and the second function, which is transformation of the parent function, are shown. Okay, let's enlarge it. Okay, here's the initial cubic function, as well as transformed function. Okay, and you can see that first we had the standard cubic function where it falls down to negative infinity and raises up to positive infinity, falls down to the left and raises to the right. But the second function we see here has the opposite behavior. It raises to the left and falls to the right. And also the point where we have zero or almost zero rate of change has been displaced 1 unit upwards. We can see that this is this point. It's been translated 1 unit upwards, and also we can see that our curve is increasing, decreasing here and here, while this curve is increasing on the whole interval. One interesting thing to notice that we can see that from my perspective, the rate of change for the red curve may be different, right? Because we can see that it's not as steep as the blue function. Okay, considering that, let's move on. And here's the question of this class. How do the graphs of y equals a times k times x minus d to the third power plus c and the same stuff, but to the fourth power related to the graphs of y to the x third power and x fourth power? And I would say that they're directly related because x cubic and x quartic functions are just special cases of this expression. This, where y equals a times k times x minus d, this is a general form for polynomial function of the third power and fourth power. Considering that, we can say that x to the third power is just some specific case of general form. And when our polynomial function equals y equals x to the third power, basically what we have here, let's look into this general form. We don't have any c coefficients, so it means c equals 0. It's only x to the third power, so we can say that d equals 0, as well as we don't have any multiple for x, so we can say that k equals 0, and a, as soon as we have just simply x to the third power, it means a equals 1. So it's positive leading coefficient. The same way about x to the fourth power. This is general form where our coefficients and positive integers, the terms, are taking zeros or 1. So here we're suggested to plot x cubic function, and then defining new parameters. Let's take a look at these parameters. By the way, here I made a little mistake. K, parameter k, would equal 1 for this variable. So basically what we can see here, when we choose a equals 1, k equals 1, and d equals 1, and c equals 0, our polynomial function would change in the following way. We would have, for example, y equals x minus 1 to the third power. This is what d equals 1 means, right? This is the formula for general case. So now d equals 1, and k equals 1, and a equals 1, and c equals 0. So we don't really have to mention them here because they're not affecting our graph anyhow. So let's use the Wolfram alpha in order to sketch this function and see how it's different from the same function, but when the d coefficient equals 0. So I'll share my screen now. And here we can see x minus 1 to the third power equals y. And we can see that this function no longer passes through xy0. The 0 of this function would no longer pass through this point, and it had actually been displaced to the right by 1 unit. So after subtracting 1 from x, our whole graph translated by 1 unit to the right. Moving back to our Nielsen textbook, let's see what they suggest us here. After implementing these new parameters, we're plotting this function, and really what we can see here, that the parent function is x cubic, passes through x0, y0, while the transform function, where we subtract 1 from x, has been displaced 1 unit to the right. Now, we can keep changing other parameters as well. So, for example, Lorraine, which parameter would you like to change next? A or K or D? Maybe C? I suggest we change parameter c, so we add some constant value to our general form. Let's say it's going to be x minus 1 to the third power plus 1. Why not? So we take c equals 1. I'll go to my graphing software, Wolfram Alpha. So I'll just adjust a little parameter here, plus 1. Now my function is coefficient c equals 1. And let's see what function will we get. Plus 1 equals. So now we can see that not only our graph been translated 1 unit to the right, but not only by 1 unit to the right, but also 1 unit upwards. You see, our point where we would have y-intercept 0 has been moved total of 1 unit in diagonal, because we subtract 1 from x, which causes a movement to the right, and we add 1 to the general function, which causes movement 1 unit upwards. Pretty much the same as standard transformations with regular functions. Is there any questions about C and D coefficients that we can adjust, Lorraine? So I believe it's pretty simple. When we change D, coefficient D, we make a translation movement in x-axis. When we change coefficient C, we make translation in y-axis. If we add positive C coefficient, we move upwards. If we add negative C coefficient, we move downwards. If we subtract D or we add negative, because in the function it's x minus D, when we choose D positive or we get x minus D, we move to the right. It's D positive. If we choose D negative, we would move to the left. For example, if x plus 1, our entire function would move to the left. However, this is what I can show you right now, x plus 1. And we look at our graph, and in fact, instead of moving 1 unit to the right and 1 unit up, we now move 1 unit to the left and 1 unit up. Okay, I hope it is clear. And now let's adjust another coefficient, for example, k, the multiple. Oh, no, let's adjust a, the leading coefficient of this polynomial function. What if we say that the leading coefficient would be -1? So I put minus in front of my brackets. And now we're gonna see what beautiful thing happens to my curve. It changes its direction. Now it raises up to the left and falls down to the right. And before that, it was the other way around. So we discovered the example when coefficient A is negative. Now I understand that the graph will change its direction, basically, right? But what if the A won't be only negative or positive, like -1 or +1? What if it also would be like multiple of 2? Let's see how the graph will change in this case. So -2, and we can see that the graph is actually becoming more steeper. Let's see if it was negative, just -1. You see the curve is like clumsy, stretching a lot. While when we put, for example, 5, -5, we're going to see that the graph is becoming more intense. Here, it's passing axis at x equals -0.5. And let's see where it passes the x-axis when we have coefficient of -1. And here it's passing at 0, right? Look. So it's less intense. So it takes more time for this curve to go down. But when we increase the A as a coefficient, for example, 5A, A equals 5 or -5, the graph would become more steeper. So basically, if we plot those two graphs on each other, they would have same inflection point, but the slope of this curve would be more extreme. You see that? There is one more coefficient left for us to examine, and it's K, coefficient K that comes. Oh, basically, right now we already discovered what K makes to the function, because a coefficient A usually takes -1 or +1 values. So we can define the direction of our end behavior, whether it's going to the positive infinity or negative infinity, while coefficient K makes this, defines the slope of our curve. If the coefficient K is big enough, like 5, 6, 10, it makes our graph more steep. But take a look at what happens if we take this coefficient as a fraction. For example, 1 divided by 2. Our graph becomes even more clumsy. It becomes even more stretched in x-axis. So when coefficient K is a fraction, our graph stretches in the x-axis. And when the K is some whole integer or more bigger than 1, our graph shrinks in x-axis, becomes more steep. I hope. Is there any more questions, Lorraine? Did you understand how these coefficients impact polynomial functions? So let's repeat it. Coefficient C defines our translation in y-axis. If C is positive, we move upwards in y-axis. Every point of the curve translates some points for number of points equal to C upwards. If C is negative, we move downwards. Then D, if D is positive, we move to the right in x-axis. If d is negative, we move to the left in x-axis. Every point of the curve is getting translated for a certain amount of units. Talking about coefficient k defines how steep would be the curve of our graph. If k is big enough, we're gonna have a very steep curve. If k is a fraction, we're gonna have a more clumsy curve. A usually takes value 1 or -1, which defines the direction of end behavior of a function, whether it goes down to the left and raises to the right, or the other way around. Usually that's what you should remember from characteristics of polynomial functions. The degree of a function defines whether we're going to have end behavior both in infinity, in the same side, or the opposite. For the odd degree function, the end behavior usually opposite. So one side would be in positive infinity for y and the other one for negative infinity. If you have leading coefficient of 1 or positive leading coefficient, your odd degree function would fall down to the left and raise to the right. And if you have negative leading coefficient, the odd degree function would raise to the left and fall to the right. For the positive degree function, if the leading coefficient is positive, we would have both end behaviors in positive infinity, and the other way around. If the leading coefficient is negative, the end behavior would end up in negative infinity for odd degree functions. Change the value of a. This we did. And now we have to repeat the same steps for quartic function. But before doing that, I'm telling you they're not much different. The only thing that all the coefficients will affect the function exactly the same way. However, the end behavior would differ because we're gonna have either both sides up, and then when we adjust the a coefficient to the negative value, so this will only affect the end behavior. So take a moment to reflect on this exercise just for yourself in order to strengthen the understanding, okay? Oh, I wasn't sharing my screen right now. That's unfortunate. Here's the reflecting questions. Please review them, and in case you have any questions regarding this, feel free to ask. So, Lorraine, any questions about transforming the quadratic and quadratic functions? Cubic and quintic functions? Okay, great. So let's move on and take a look at the example number 1. Using reasoning to determine transformations. Describe the transformation that must be applied to y equals x cubic to graph y equals -8 times 1 over 2 times x plus 1 to the third power minus 3, and then graph this function. So first thing first, when we are working with description of a transformation, we have to bring the function that we are given with to the general form that we learned. And then in this case, the general form is a times k times x minus d to the third power plus c. And here we can see for clear that we're missing some brackets over here. And in order to bring this expression to the second one, we would like to factor out from these brackets what we don't know, what we don't want. Okay. So, considering that, what is the stuff that we don't want to see here? We don't want to see any coefficient in front of x. We want to see x plus some constant value in the brackets on itself. So that's why we are going to factor out 1 over 2. While factoring 1 over 2, this 1 would turn into 2, right? Because 1 divided by 1 over 2 will give us 1 times 2 equals 2. So after factoring out this coefficient, we can see that our function took a general form. So, and this is a good way to remember k for coefficient of x, k for coefficient, okay? And to begin with, we have to eventually we have to describe transformations that are applied to parent function x to the third power. First of all, we have to define the main characteristics of x to the third power function. So this is the graph for x to the third power. And to plot this graph, I would certainly find y-intercept, and it would be simple. I just substitute x equals 0. Then I would take a look in the odd degree of this function and assume that it's going to have an end behavior like falling to the left and raising to the right. Then I would have to find few more points to the left and right from this y-intercept in order to plot this graph properly. So Well, now we understand how the x cubic function would look like, and now let's mention the coefficients that are taking place in our transformations. First of all, we have a equals -8. This is the one in front of the brackets, right? And it's negative. Then we have k equals 1/2. Then we have d equals +2. But look, remember in the initial function we have, for initial formula, we have -d, and here we have +2, so d is -2. Does it make sense? And then finally c -3. Exactly what they say here. Basically, what is happening to our parent function? It's getting stretched by a factor of 8 and reflected in the x-axis. So it means the end behavior would turn to the opposite way. I'll use the red color to visualize it on this graph. So now we're going to have end behavior like this. Two ends reversed and stretched by a factor of 8. It's going to be stretched in y-axis, so it's going to get even more steeper. And now it's getting horizontally stretched by a factor of 2. Remember, we discovered this effect of this coefficient on the shape of a graph. So horizontally stretched by a factor of 2. And finally, d -2. Remember, d is the coefficient that affects the position of the graph in x-axis, while c defines the translation of a graph in y-axis. So this graph would be translated 2 units left and 3 units down. So don't get confused when trying to understand what d and c coefficient does, because if it's negative, follow the coordinate axis. For x, it's going to go to the left. If it's negative for c, follow the coordinate axis. For y, it's going down. So now we can make a statement that our graph is going to be vertically stretched by a factor of 8 and reflected in the x-axis, or is reflected because the leading coefficient turned from positive to negative. Horizontally stretched by a factor of 2, which k coefficient gives us. Horizontally stretched means in these axes. So it's going to get stretched vertically and horizontally. Also going to be translated 2 units left. So every point of this function would be translated 2 points to the left. And 3 units down. Every point will also be translated 3 units down. And here, this is where a k and a coefficient take place, right? Because as soon as it's getting stretched by a factor of 8 in y-axis, vertically, right? That's where this coefficient pops up. And it's gonna get stretched by a factor of 2 horizontally. This is where this coefficient stretch up. So basically, for every point of the initial graph, we're gonna have a following pair of new points for the new graph. First of all, we're gonna have every x doubled, every y 8 times, and y values are reflected in x-axis, so opposite side. Here's the set of points for y equals x cubic. These are the points we have for the parent function. Meanwhile, these are the points we have for the transform function. And you can see the transformations applied here. 2 times the x-coordinate, -8 the y-coordinate, and that's as simple as that. This is when we're performing the stretches, reflections, and compressions first. Multiply the x coordinates of the key points by 2. Multiply the y coordinates of the key points by -8. And now you get a new set of points for your function. Moving on, after stretching horizontally and vertically, now we can perform the translations at last. Because after defining the new shape of our function, we can translate this shape by the required number of units. And it's very simple only by looking at the d and c coefficients. So performing the last translations, subtract 2 from the x-coordinate and 3 from the y-coordinate of each point on the red graph to obtain the corresponding points on the blue graph. Here you can see the set of points we get after translation, and translation is just type of linear transformation, so it's pretty simple as that. Solution B, in which we simplify the equation first. Take a moment to look at this. So, are you ready, guys? Looking into this particular example, we can notice that we could have simplified this transformation even more, because we have coefficient of 1/2 factoring it out will give us simplification of a and k coefficients together, right? A and k, we group them up and we only, as a residue, we have -1. So only transformations we would have to apply in this case without stretching the graph. We only would inverse it or reflect it over the x-axis. Okay. Again, this is exactly what we can see here. Our graph didn't get stretched a lot, and that's because the x and y stretch compensated each other. And basically what we have left is only a translation movement, right? Translation and reflection over the x-axis. So it means that the curve was concave, going up to the left and falling down to the right after applying the negative leading coefficient. And the last step was to apply the translation, because the stretch basically compensated itself. Here you can see that we don't have any stretching, because k and a coefficients are not impacting our function in that way. The only way they impact is here, changing the direction of our graph, because the leading coefficient is -1. Please take a moment to note down this simplifying of equation example, solution B, because this is, as for me, most convenient one for your future studies. Copy this particular example. Take up to 5 minutes to do that. So Lorraine, do you need extra time to copy down this example? Okay. Have you finished on this page? Okay, because there's number of points here. Do you still need this page or this one? I'll zoom out so you have both pages. So, Lorraine, how things are going? Yes, you finished copying down, or yes, you're still copying down? Okay, great. Let's take a look at this interesting example where we are defining the roots of quartic function, because this is really important to know how to do, because roots will help you to find the zeros of this function. So, and for your future studies, solving quantic function is useful. First example, we're going to use algebra. Determine the x-intercepts of the function y equals 3 times x plus 6 to the fourth power minus 48. At first glance, it looks terrifying how to find the x-intercepts here, but in reality, it's not as hard as it looks like. So first, we substitute y for 0, 0 for y, and trying to solve it. Then we have to group up all the terms that have no x in it on one side, and all the terms that have x in it to the right-hand side. Exactly what we did here. As soon as it was negative 48, we basically add 48 to the left and right-hand side. That's how I get 48 equals 3 times x plus 6 to the fourth power. And basically what we're going to do is to use the inverse operations in order to isolate this cubic term, x plus 6 to the fourth power. So we add 48 to both sides. Now we divide by 3 both sides. Now we get 16 equals x plus 6 cubic. Now we're taking a fourth root on both sides in order to get rid of this complicated exponent. And remember, when we're taking roots, we're getting two solutions for positive numbers, because we're getting two solutions in case if this root is an odd degree. If we take a root of fourth power, the outcome could be plus minus 2, for example, because as well as negative 2 to the fourth power could give us 16. So positive 2 to the fourth power gives us 16 as well. So after getting rid of this fourth degree exponent, we are left behind with expression plus minus 2 equals x plus 6. Any even root of a number has both a positive value and a negative value. So now we basically have to solve two separate, simple equalities. 2 equals x plus 6 and negative 2 equals x plus 6. By doing the inverse operation, subtracting 6 from left and right hand side. On the left hand side, we get negative 4 equals x, when this root equals positive 2. And when this root equals negative 2, we get negative 8 equals x. So we're getting two x-intercept points in negative 4 and negative 8 x values. Please, Lorraine, take a moment to note down this solution for determining roots of quartic function. While determining roots for cubic function, you're going to see that we have taken root of the third power here. That would be the only difference. And when you're taking the root of the third degree, you have only one solution, as soon as you couldn't have negative value there, so you take only positive one. Let's take a moment to note down this example. Please, Lorraine, let me know once you finish. So, Lorraine, how's doing? If you're done, I would like to skip this example number B when we use a graphing calculator. I don't really support that idea, but let's take a look at what they show us here. So we're using a graphic calculator, entering the equation into graphing calculator. Then basically we define our transformations with respect to the parent function, right? So stretched vertically or horizontally, and then vertical translation by 48 points. Then we define the coordinate transformations, new locations of the turning points, defining whether the graph opens up or down, so basically what it says here, we apply all the transformations to our parent function, determining a new location of critical points like turning points, etc. Adjusting the windows and finding new zeros. And here you can see as the answer would be -8 and -4. Okay, this method has a right to exist. However, it is much more efficient to know the algebraic way of solving quintic functions, because you won't always have a graphing calculator by your hand, right? And this type of equations can be solved easily using algebraic way. You can see it's not many operations to perform, so why not to use algebra when you can? And in summary of today's class, basically the polynomial function, they always have this general form. Please note down this general form of any polynomial function where n defines the degree of your exponent, the greatest exponent of your polynomial function. Whether it's cubic or quintic or whatever, general form would be as follows: y equals a times k times x minus d to the power n plus c. And the polynomial function with such form can be graphed by applying transformations to the graph of the parent function. This is what we covered today. We're transforming the parent function with respect to these coefficients when we know what these coefficients do. So where n equals en, where n belongs to the natural numbers, that's what we say about exponent. Exponent cannot be a fraction or irrational number. Right now, we work with exponent only as if it was a natural number. Each point xy on the graph of the parent function changes to x divided by k plus d and a times y plus c. Hello, Yasser. Welcome to the class. You're right on time. Actually, not really. Unfortunately, every class we take attendance, and I would have to consult with the principal of the school whether I can treat 2 hours late as attended. I'm gonna have to consult regarding that. When using transformations to graph a function in the few steps, you can apply a and k together and then c and d together. That's also good choice because you can make it in many steps. Please review the summary of today's class, and we're gonna have a 15 minutes break right now. And in this last hour of the class, we're going to practice some problems. So guys, our 15 minutes break is done, I believe. Are you with me? Can I continue to the practicing exercises? Guys, are you with me? Guys, are you with me now? Okay, guys, I believe I gave you enough time to rest. And we're going to proceed to practicing exercises, and please use this time to see the questions and ask your questions, okay? Because this Friday we're gonna have a unit test for this past 2 weeks topics. And before we start our practicing exercises, let's repeat one more time what you need to know. So in this general form for polynomial function, value of a, let me use some circle to highlight it. Value of a, the value of that represents a vertical stretch, compression, and possibly a vertical reflection. Possibly because it depends on the sign of this leading coefficient. And then we have the k value. The value k represents a horizontal stretch compression, possibly a horizontal reflection. Then we have the coefficient D. The value of D represents a horizontal translation. And finally, we have value C, constant C. And C represents the value of vertical translation. Okay? I hope it's clear. And I suggest we skip this part with simple question. Here, this is simple one as well. So let's take a look at this one example, number 3a. Describe the transformation that were applied to the parent function to create each of the following graphs. Then write the equation of the transformed function. The parent function for this case is x to the third power equals y. And when we look into this transformed function, let's note down right away that the left side is falling down and right side going up. So it means the leading coefficient A is a positive number. And then what about transformations? We know that this point on the x to the third power, in the original function, this point lays in the x0, y0, this little inflection point. Yeah, like this. And here we can clearly see that this point is being translated from 0 to this point, -3 and -4. So I can say that my coefficient C, which represents for y displacement, is -4, 4 points down, and my D is -3, 3 points to the left. And also I have coefficient K left. K and A, we can see them as multiples. Actually, I don't see any stretches here. For these points, let's fall back for a second and take a look into how we should see the effect of K and A. Basically, when we apply this K and A multiples, they're going to be represented in X and Y coordinate transformation, right? And for a particular case where we have, in a particular case when we have A equals -1, it affects the Y coordinates, so we multiply Y, and when the K affects the X value, right? If we look in the very first example, yeah, right here, 2 and -8. In this example, 2 and -8, -8 is an A value, and 2 is the transformation of a X coordinate. And we divide by 2, we multiply the X coordinate by 2. If we multiply by 2, we divide by 2. So, moving back to the problem we have here. So let's define whether we have k value in here. K should affect the x coordinate, right? And if the parent function was x to the third power that passes through the beginning of the coordinate axis, we translated it, and we know for sure that a is positive, and here we can see when x equals -1, y equals 4, so we have to make a corresponding x and y coordinates from the parent function with respect to some new x and y coordinates in transform function. We already know for sure that it's getting translated for -3 and -4 in x and y axis. So if we apply these translations to these points, we're gonna see the coordinates for the parent function, and then we would be able to see if we have any a or k multiples, right? Because a is multiple of y, while k is multiple of x. And let's take point -1 and 4. If we apply these transformations but in inverse, so instead of subtracting, we add them to these coordinates. So we would have when x equals -1 for transformed function, the parent function would have 2, and for y equals 4, the parent function would have y equals 4 plus 4, 8. So x equals 2, y equals 8. So now we have this 2 pairs of points. For the parent function, we have, remember in the last example, we first applied all the transformations and then we made the translations. And when we are trying to define from the end, like we already have the transform function, we're doing the other way. We apply the translation first, then we define the transformations. And here for the parent function, we have points 2 and so x plus 3, it's 2, and y would be 4 plus 4 is 8. 2, 8, and on the opposite side, -1 and 4. So 2 and 8 is the points for the parent function, while -1 and 4 are the points for the transform function. And you can pretty easily check it. 2 and 8, you substitute 2 into this, y equals x to the third power, and that would be equal 8. So it's right. So rather than translation, I don't see any great transformation that may be applied to our function. So because if there were some additional transformation, then this ratio of a cubic form would be changed because our function would be stretched or compressed in y or x-axis. But as soon as this transformation basically linear, we can say that A is positive because the direction didn't change of the end behavior. So we're gonna have A plus 1 and K, in order for us not to have any impact on the x-axis, the K should be 0. So my transform function formula, considering all of these coefficients, would be y equals basically plus 1 times x subtract or plus 3, because d is -3, right? Plus 3 to the third power. K, or sorry, K is not 0, K is 1. That's my mistake. K should be equal to 1. We also don't see any vertical mirroring of our graph. So K is non-negative value. So we're gonna have it like this: plus 1 times plus 1 times x plus 3 to the third power, subtract c minus c, right? That's the way it looks in the in general form, or plus c, sorry. General form is plus c, but in this case c is negative value, so we get -4, -4. So my answer would be as follows: the transformations that are applied to this function are translations, as well as nothing else. Because we only translated the initial graph and didn't reverse it or stretch it anyhow. So you can see this clear transform function formula: x plus 3 to the third power minus 4. Let's take a moment to note down the final answer for question number 3A. And remember, always follow the algorithm that is mentioned in this class. First, you do the transformations, then you apply translations if you're transforming the parent function into some other function. If you work the other way around, first look into the translation if there is any, and then define the transformations. It is easier to look for translations because transformations won't change 0, x, y, 0, but I mean, for cubic function, they won't change position of this origin, where transformations won't change this point. Even if you transform your function a lot, it will still have x0, y0. But if you translate your function, then this point would move away. That's how you can understand all the translations. Okay, guys, are we ready to move on? So right now I suggest you, it's my little advice for you, because we're gonna have a unit test this Friday. Mhm. So I suggest you to practice this. Number 9, determine the x-intercepts of each of the following polynomial functions. Round to 2 decimal places if necessary. This is exactly what we did in today's class when we were doing the inverse operations in order to find the x-intercept. So for example, a, it would be 2x plus 3 to the 4th power minus 2 equals 0, right? Now we put -2 to the left, we divide by 2, and we take a square root of 4 in order to find the solution. So we're going to have 2 equals 2 equals 2 times x plus 3 to the 4th power. Now we divide left and right hand side by 2. So we get 1 equals x plus 3 to the 4th power. Now we take a cubic root of 1 and as well as cubic root of x plus 3 to the 4th power. Here the 4th power is simply simplified, and here we're getting two answers, plus minus 1. So it's x plus 3 equals plus minus 1. And we have two solutions out of it, number 1 and number 2. If it equals positive 1, x equals -2. If it equals -1, x equals -4. Here are our two x-intercepts. Please take a moment to note this down and solve as many examples from this exercise as you can, because I'm pretty sure something like this is going to be in your unit test. Please, and while we still have 20 more minutes of this class, please use it to ask me some questions so I can help you to prepare to a final unit test at the end of this week. So Yasser, how are you doing? Hey Yasser, how are you doing? Do you need any help? Do you have any questions about this exercise?